So I conveniently left my notes at the table, and that's just as well. Better to speak to you than to read from things anyway. So I want to introduce the panel quickly, and then we'll get going with our keynote. So we'll start on the end. Dr. Bridget Scanlon is a senior research scientist at the Bureau of Economic Geology. She's a hydrogeologist and very well recognized internationally. She's an AGU fellow, I think one of 2 or 3 in our school. She's been the Birdsall-Dreiss Lecturer for GSA and many other honors. Bridget is deeply recognized as one of the leading thinkers in hydro and hydrogeology. Ben Smith is a brand new PhD student. He just passed his exams to qualify 3 days ago, was it, Ben? So, and he's a rock guy. He looks at carbonate rocks in the outcrop, and Charlie Karen's student, and I'm on Ben's committee as well. Dr. Svetlana Konikova is a physicist and a mathematician who got captured by the dark side and did her PhD in economics and a postdoc in Germany and Belgium. And she's an energy economist and leading a major integrated team of engineers, geoscientists, and economists studying shales and shale gas reserves and production in the U.S. and beyond. Professor Charlie Cairns. Dr. Charlie Cairns is a professor in the department and holds some sort of honorary appointment at the Bureau for life, as far as I can tell. But, if he doesn't write often, but he writes very well. And so when Charlie writes, he wins best papers. I think he has the most best paper and best poster and best talk awards of anybody I've ever known. He's certainly decorated by the professional societies, including the Twenhoffel Medal and others, recognized for his work. And if there's an expression, he who sees the most rocks wins, Charlie wins, hands down. Seen a lot of rock. And finally, Secretary Koonin, Steve Koonin, is a good friend that I met many years ago now. He went to Caltech when he was 5 years old. Actually, he might have been a little older than that, but not much. Was provost of Caltech, I think in his late 30s, maybe 40, and was chief scientist at BP for a few years to sample that, became Undersecretary of Energy in the first Obama administration, and now runs a major, very fascinating program in New York City that he worked with, I think, Mayor Bloomberg to form originally, and we'll hear a little bit about that potentially, but Steve is one of the brightest and most global thinkers I know on energy and things related to that. So we appreciate you all being here. Steve will give the keynote kickoff talk, and then I'll moderate a discussion among the panelists. And I'll remind you, there are cards on your tables, and those in the back, grab cards if you want. Write down a question or two. I definitely will leave time to get to the questions that come from you all in the audience. So, Steve, it's all yours.
Thank you, Scott. So my task is to look forward several decades, energy, minerals, and water, and try to understand what the implications of that view are for the geosciences. These are very complicated subjects, and so I'm going to try to steer between generalities that are so general that they're useless and specific predictions that are almost certain to be wrong. We'll see how well I'll do. So energy, minerals, water do not exist in a vacuum. They are important parts of society. And so before we start in on those specifics, we should understand the context. And Mark Zobek talked a little bit about this morning. I'd like to give a somewhat different, perhaps complementary view. Demographics are really important. Global population growing from current 7.3 to about 9.7 billion people by mid-century. The developed world, which is about 1/7 of the current world, about 1 billion people, is aging. So we see most dramatically in Japan and China at the moment, but certainly in this country as well. The developing world, I was just in Malaysia a couple of weeks ago, the number of young people in the developing world is just staggering. And then finally, urbanization is a trend. My own focus these days is on cities. The world is urbanizing at the rate of 50 million people a year, so that's 6 New York cities. We're currently at 50% urban globally. That number will go to 70% by the middle of the century. The economic dimension, we're seeing the development of most of the world, not the 1 billion people in the developed world, but the rise of the rest of humanity. That induces a growing demand for resources. Energy demand will be up 50% from today. Mark said a factor of 2. I think it's somewhat less than that. And at least for the U.S., we're going to see a leveling of the playing field. Right now, the U.S. is about 4.5% of the global population. We're about 19% of the global GDP. So we're out of whack by about a factor of 4. And the second law says you cannot sustain that out of whackness for very long. That's got profound implications for how we think about ourselves as a society in the U.S. and how we make our way in the world. I don't think the political sphere has caught up with that yet. Energy. Right now, fossil fuels, 80% of the world's energy supply. They are the most reliable, the cheapest form of energy. In environment, more people means more environmental impacts. David Silberman, who's an economist, environmental economist at Berkeley, once told me that the only humans who don't pollute are dead ones, and that's not even obvious. So we've got to manage those. And of course, the world's politicians now believe that they're going to stabilize the climate by reducing greenhouse gas emissions. How real that aspiration is remains to be seen, but it is certainly an important part of the future going forward. Technology progress, I think most relevant to these subjects, energy, water, minerals. Informatics is moving very rapidly. Our ability to acquire, transmit, store, analyze vast amounts of data. Already in the geosciences, we heard this morning about TextNet. I would put the Argo system measuring the oceans as another example. We're seeing revolutions in materials, our ability to design at the molecular level, to manufacture at the few micron up to millimeter level, wondrous advances in being able to design materials effectively. And then biology. When I was a kid in school, biology was entirely descriptive. It is now very close to engineering at the molecular level, both at the genetic level, the protein level, and so on. So these things will form the technological background against which energy, water, minerals will play out. I think more generally, we're going to see greater regulation to try to rein in the environmental impacts. We're seeing a globalization of goods, people, ideas, capital. And these are the features of the landscape in which the subjects of interest are going to play out. So what does all this mean for geosciences? I'm going to start with energy, and then we'll move on to water and minerals. Energy. Some of the givens, things that you can say almost with certainty over the next 30 to 50 years. Cost and scale are really important. I learned that from the Switch movie, most importantly. It's a great movie. The carbon constraint is also going to be really important, but those are not the only considerations. Reliability is an important factor. The world has very little tolerance for electricity outages, at least in the developed world. The carbon constraints, I think, are generally not recognized for how severe they are. I show on the left there some emissions trajectories that the IPCC adopted as baseline scenarios. By the way, the vertical axis should be gigatons of carbon, not gigatons of CO2. You see the historical trajectory and the different trajectories of what would be required in order to just stabilize the atmospheric concentration of CO2. It's basically shown on the right, the atmospheric concentration or the radiative forcing. You can see, if you pay attention, for example, to the green trajectory, to just stabilize human influences on the climate at what they are currently, we've got to take emissions to actually less than zero by 2070. All of the other trajectories also clearly go down, except the blue one, which doesn't. All right. We are not making much progress. There was this conference in Paris, COP21, last month. The emissions trajectories on the left, the gray shows the historical, those little yellow bars in the right show by how much the voluntary reductions would amount to by 2025 and 2030. Remember, this is the emissions. The emissions are in some sense the derivative of the concentration because the CO2 lasts for a long time. If you look in the right panel, what do we need to do in order to get to zero by 2075? Those are the blue trajectories, and I would argue that that's a pretty heavy lift for the world. It becomes even heavier when you start to consider what's going on in the different countries. This chart's a little bit old, it's about a decade old, but energy doesn't change very rapidly. This shows per capita emissions against GDP for some 25 years of data, and you can see that today's global average is actually about 6 tons per capita of emissions. We need to get down, as I said, effectively to zero if we're going to stabilize human influences on the climate, never mind stabilizing the climate. A second energy given is that the energy system will change slowly. There are very fundamental reasons why that's true. Energy systems require large amounts of capital. They live for a long time, 50 or more years. They produce commodities, and so people are reluctant to take technological risks. And of course, we need to have interoperability between different parts of the energy system. Vehicles, fuels, fueling infrastructure all need to play together. That's played out in the data. Here's the US energy supply over the last 160 years. And you can see, yes, it does evolve from wood to coal to oil to gas, nuclear, a little bit of renewables at the end. But the evolution takes decades in order to make a material difference. Another energy given is that it's a local discussion. What individual countries or even regions of countries decide to do depends upon their resource endowment, the existing infrastructure, the climate, the mix of activities. What's good for Syracuse is not what will work for San Diego and will not work for Sri Lanka. All right, so there's no one silver bullet here in trying to meet the energy challenges. And then finally, as I start to go through the various energy dimensions, cost-effective efficiency is good for all seasons. That's not efficiency at any cost. Efficiency for hardware, operational efficiency are elements of what's going on here. So let me talk about transport, which is one of the 3 elements of energy: transport, electricity, and heat. Transport, we're already seeing autonomy and connectivity in the vehicles. You can start to buy vehicles that can drive themselves on the highways or park themselves and so on. This will progress, I believe, faster than most people realize over the next decade or two and profoundly change the way we think about personal transportation. If the world is going to take emissions to zero, no oil, no coal, no gas, zero, all right? If we don't give up on oil instantly, which is not going to happen, we can make the vehicles much more efficient. I think probably a factor of 2 relative to where we are right now. Mass is a big lever in getting vehicle efficiency up, reduce the mass, better internal combustion engines, progressive hybridization of the fleet driven by electricity. For oil, the supply curve is your friend. We're going to see opportunities further in geosciences, exploration, reservoir characterization and management. More tertiary recovery will go on. There are good science opportunities there. And then we'll just march up the supply curve. Offshore, Arctic, oil sand, shale oil, oil shale, et cetera, et cetera. If and when we give up on the hydrocarbons for transport, we will see fully electrified light-duty vehicles. We can do that now. It's not a major hit on the electrical power system, maybe a 20% increase. The batteries are starting to come along. You can buy 200-mile range EVs right now. For the heavy-duty vehicles, you got more of a problem. You can't give up on the hydrocarbons because you need the energy density, but biodiesel, perhaps hydrogen, are ways of fueling the heavy-duty vehicles, again, without emissions. There will be, I think, as we go through this transition, if we go through the transition, some unexpected consequences. 2 that come to my mind is that low oil demand will create lower prices, and that will perhaps extend the transition to zero hydrocarbon world. And for you all, perhaps in the geosciences academic world, you'll see the end of commercial support for geosciences. And it's probably worth thinking about what the Jackson School looks like in that limit. Let me say something about electricity. It's common to compare different sources of electricity by what's called the levelized cost of electricity, LCOE. And there is a sort of typical chart. You see various methods of producing electricity measured by their cost per kilowatt hour, in this case, cost per megawatt hour in dollars. Nuclear on the far right, CCS with natural gas combined cycle, just moving from the right to the left, et cetera, et cetera. Notice that these technologies have different balances of capital versus operating expenses. That's important to notice. But it's a lot more than just the cost of electricity. Intermittency, dispatchability, land use, water use, local environmental impacts are all important. Absent carbon constraints, if the world doesn't get serious about emissions, we're going to see coal, gas, and fission dominate. Hydro is pretty well tapped out around the world. Again, for geosciences, we've heard a little bit. Hydrofracturing fluids, be nice to get better fluids than we've got right now. Integrity needs to work on that, and the lifetime of the wells. Methane is commonly discussed as a bridge to a low-carbon future, but there are serious academic studies that say if the world ditched coal in favor of all methane, the impact on the climate would not be noticeably reduced because of the methane leak rates. Methane is a powerful greenhouse gas, because of the loss of the coal aerosols, which are helping to keep the planet cool, and because of increased energy demand. So I'm on the fence in terms of the climate impacts of a methane world. Renewables, solar and wind, very popular among people who don't understand the energy system very well. I think we need the geoscientists to help us with the weather statistics, the variability, and particularly the covariability. If we're going to run the country on wind and solar alone, you need to know when it's cloudy in North Dakota, how much sun do you have down here in Texas, for example. Land use is a serious issue for these renewables. A number I like to quote is, with current technology, 1 gigawatt continuous solar at utility scale, so that's 5 gigawatts peak, roughly, takes 50 square miles. So 7 miles on a side to produce the equivalent of 1 fission reactor in terms of power and energy. Local environmental impacts, you start putting up lots of wind turbines, and they certainly affect the local environment downstream. Because of the variability of the renewables, we need massive energy storage if these are going to be a significant fraction, let's say more than 20% of the grid. You also need extra generation, because you got to generate the energy you're going to use at night, store it, and then use it. Or we need fossil fuel backup, but that violates the dictum of no fossil fuels if you want to go to zero emissions. And then finally, for these, you need transmission infrastructure. People tend not to live where the wind blows or the sun shines too much, and you need to put in the transmission lines to get it to where the demand centers are. Geothermal, I'm not sure I should even venture to say much about this in this audience, but understanding where the deep resources are would be a lovely thing to be able to do, and of course the technologies to be able to access that resource would be wonderful. For base load, the renewables are not base load. For base load, nuclear, I think most people think, has got to be a major part of the picture. You might worry about the uranium resource. I don't. The world's got plenty of uranium. Uranium fuel costs are a small part of producing nuclear power, and we can almost economically extract it out of seawater at this point. I would worry about, if we don't reprocess, the integrity of the waste repositories for nuclear, seismic hazard for the nuclear reactors, and of course availability of water, since basically the reactors are just boiling water. CCS, I know a great interest here. Beyond the additional cost, I worry about the reservoir integrity. The lifetime of CO2 in the atmosphere is 300 years, roughly, and so if you're leaking at more than 0.3% a year, you're not really doing much good. And so I don't think we've been able to demonstrate yet integrity at that level, though I'd be happy to be proven wrong. All right, let me talk about heat, the second of the three dimensions of, or the third, I'm sorry, transport electricity, heat. Absent carbon constraints, it's gas, gas, gas. And one of the things I would ask is, can we produce shale gas resources beyond the US? I ran a session in Japan back in the fall, had lots of international folks from the hydrocarbon business, and what I learned is that the resources in the rest of the world present various challenges in trying to produce them at the scale that we are able to do in the US. Some of it's got to do with geology and fractured bedding that isn't very conducive to horizontal drilling. A lot of it's got to do with water availability, and a lot of it's got to do with societal factors like access to the distribution infrastructure. The pipeline we heard about here in Texas, other countries have a hard time pulling that kind of thing off. If we've got carbon constraints, what do we do about heat? For residential, well, we can do better building design. We can put solar hot water heaters on the roof. That works pretty well. Carbon-free electricity to heat, so imagine that nuclear reactor or solar farm somewhere outside of the city producing electricity, sending it into the buildings, turning it into heat by resistive heating. That's not very efficient. You throw away 2/3 of the energy that way. You could try to do district heating, cogen, not allowed to use gas because no hydrocarbons. Small modular reactors in the middle of cities. Biomass, you can't make enough of it. Industrial, I have no solution there. Biomass, I don't know what. So as you think about an emissions-free world, I think heat is going to be the barrier to getting there, should the world decide to go there. A little bit more about geoscience aspects under a carbon-constrained world. I think there is a future in what's called MRV, monitoring, reporting, and verification for carbon treaties or carbon agreements. How much are the Chinese really emitting, and how do we know that? And can we know it confidently enough to be able to challenge a treaty? We need to understand the carbon cycle. We need to understand transport of greenhouse gases from their sources through the atmosphere, and we need to be able to do it with both in situ air sampling as well as remote sensing from spaceborne platforms. Adaptation, I think that this is the way the world is going to go. I wrote an editorial about that in the New York Times about 2 months ago and took a lot of flack for doing so. And I would ask, the geoscience questions here, what should we be adapting to? Can we do local climate forecasts, right? People are really worried that the sea level in New York City is going to rise up and swallow Manhattan Island. The actual historical rate for the last 160 years is a foot a century, to which we have been adapting to very well over the last century and a half. But some of the climate model predictions go up to a meter over the next century or even more. Can we refine those predictions to give the people responsible for the infrastructure a little bit better guidance? And then finally, what are the adaptation strategies? In mitigation and emissions reduction, we have the famous wedges, which were basically technologies that could be deployed at some cost to save various amounts of emissions. What is it for adaptation? What are the modes? What are the costs? What are the timescales? Nobody's thought that through yet. When I was in the Obama administration, I wasn't allowed to say that word, geoengineering, but now that the National Academies has produced a report about a year ago, I think it's become a topic that one can talk about in polite company. Air capture, carbon management, either by chemical or biological means. I have issues with the scale and cost. When you think about how much carbon you got to pull out of the atmosphere, or costs estimated at $400 or $500 a ton of CO2, this is currently a non-starter. And then many people talk about beneficial use for CO2, and I have a problem there with scale and energetics. To set scale, the country right now, and maybe even the world, I'm not sure, uses a grand total of 60 megatons of CO2 per year for enhanced oil recovery. It's the biggest use. Maybe you could get it to 100 megatons of CO2. The country's emissions are 5 gigatons of CO2, so there's not enough use there to soak up the CO2. You want to turn the CO2 into some other useful material. There is no other material on the planet that has as much volume as CO2 that we emit. And also CO2 is a low energy molecule. It's the end product of combustion. You want to turn it into something useful, you're going to have to add energy to it. And where's that energy going to come from? So I got a problem with carbon air capture. Solar radiation management, aerosols in the stratosphere, okay. You really need to understand the system and how you're perturbing it if you're going to go down that route. And so baselining, a detailed understanding of the environment or the ecosystems before you start into that is really important. Okay, let me say a few words about water, about which I know much less than I do about energy, and I hope the panel will be able to chime in at some point. My impression is in the US, it's mostly a social, legal, economic problem. California water crisis, 90% of the water is going to agriculture, only 10% is going to human use. I think we need to understand better the historical and future variability, again at the local or at least regional scale. Frequency, magnitudes of droughts and floods. We also need water for thermal power, so this starts to intersect with energy. In the US, we do a pretty bad job of conserving water, recycling it, storage, reuse. My recollection is in Europe, it goes around 6 times before it finally gets discharged. In the US, it's like 1.5 times. So this is just a question of political will and economics. I'd like to understand how much water is in the ground. I think somebody mentioned that this morning. How do we more efficiently do reinjection and storage of water? And then finally, desal. Desal technologies are within a factor or 2 of being at the thermodynamic limit for the energy required. They're not that expensive and they scale well. I did a calculation once. The heat from 2 gigawatt reactors would desal all of the water that Los Angeles County uses. It's not so bad. But people are worried about environmental impacts, withdrawing the water and wiping out fish eggs, and the brine tailings going out into the ocean and messing up the ecosystems there. So I think some serious experiments, measurements, study about that would probably be a very good thing to do. Last, minerals, about which I know even less. I'm pretty sanguine about them because I think there are lots of levers that one can pull to deal with mineral problems. We can foresee the use of exotic minerals in batteries, lithium, magnets, take the rare earths, PV, power electronics, gallium. They all use exotic materials, but there is recycling, of course. There is the supply curve, and there is the push to make these uses use earth-abundant materials as opposed to exotic materials. And then finally, there are material science opportunities to develop alternatives. So I'm not so nervous about minerals. I'd be happy again to be proven incorrect. With that, thanks for your attention, and we'll get on to the panel.
Thank you, Steve. That was a great tour. So let's get started. I'll ask a few questions. Again, if you have questions to write down, please do so. We'll collect them. So Charlie, I'm going to start with you. You've seen a lot of rocks. Energy, water, minerals. Why does it matter? You know, why do rocks matter even for geologists anymore? What is it that you learn, and what are some of the new technologies that you see coming that'll matter in these topics?
Yes, I saw that question last night, so I've had 2 minutes to think about it.
That's more warning than I usually give you.
whatever it was. But really, you know, I mean, to me, when I think about what we do as geologists with rocks, it's hard to communicate. We always need to do a better job of communicating that with the rest of the world. But it's, you know, to climate, you know, which might be reading the Times or the New York Post or something. I mean, it's like reading a novel. You know, the depth of information and the history that's recorded in the rocks that we read is something that most people, you know, really do not begin to appreciate, I would say, even well into graduate school. We work with people, we study rocks, we look at rocks, but you know, when I'm looking at a rock and I'm talking to one of my students, you know, it's the usual game, you know. I'm seeing something and they're nodding like, yeah, okay, will you just leave me alone if I say, yeah, I see what you see? And I say usually not, but there's just a huge depth of information, and we're starting to see that play a role in a whole range of things other than just energy. We start to use a knowledge of rocks. A lot of the people that study climate say that some of the best records of the Earth's climate and of changes in things like sea level are recorded in tropical limestones, which is why I'm keeping going down to the Caribbean. But that the knowledge and the information that's recorded of the sea level history there is way richer than some of the controls that we have from straight geochemical constraints. So there's certainly things that we can learn there that are critical to our knowledge. But I think that we do people a huge service to learn an understanding of time. A lot of the things that have to do with things like understanding climate have to do with understanding the time averaging that geoscience tries to teach people. Scale is another one, you know, and I look at, you know, I listen always with great interest to some of Sergey's observations about seismic data, but what he sees in seismic data and what I see in seismic data are two largely different things. You know, the level of resolution, the images that I'm looking for after studying cliff after cliff after cliff and now get my knee replaced. I mean, there's lots of things that you really, you know, you just have to learn by seeing these things, and that's the students that come through here that get an appreciation for those rocks have, in my book, always had a very, very bright future and gone forward and led very, very interesting discussions with people.
Tell this group a little bit, not everybody probably knows, a few of the new technologies being used on the outcrop.
Yeah, we're having a great time, and I'm planning on bringing out a drone to the next field methods class that we go through. We've been able to bring in LiDAR technology. We're starting to bring in, with Chris Sam and a bunch of people at the Bureau, we're doing more 3D photogrammetry, doing remote drone imaging. We're doing also hopefully getting hyperspectral capabilities into these imaging tools to where we can actually, you know, see things and observe features, you know, in the rocks that we just never could see before. Things that we used to try and learn, and it would just frustrate us to no end. Now we can walk out and start doing very high-level work within a matter of a week or two that used to take pretty much somebody their entire research career to learn. So things are happening very fast. It's certainly all in the big data realm. I never really worried about that much, other than, you know, pretty much every year you're burning out computers or becoming kind of somewhat unimpressed by some of the capabilities we have here, because every time we throw the full data at it, it's crushed. You know, it doesn't take almost any time to crush one of these computers, but that's because we keep visualizing and seeing things that we want to see more, so we keep learning more. But, you know, the students that get into earth science, I think there's a, you know, really fascinating use of new technology that we're trying to introduce them to, and it's exciting. You know, it's not just biosciences that are doing confocal microscopy. The geologists are doing it as well.
Ben, you're getting into this field and you're revisiting some outcrops that some people made a real mess of 25 years ago, but you got new technology now. Charlie's just talking about it, some of it on the outcrop, and some things in the lab too. The president mentioned at lunch the new medical center and the research and the technologies that go on there. We use them all on the rocks. What are some of the kinds of things you're thinking about doing now that we couldn't do 25 years ago to tear this apart?
Well, I think Charlie hit on some of the specifics for me. You know, the idea of using drones or LiDAR or new technology. But I think probably the most interesting thing is a combination of something old and something new. I think some of the morning panels we talked about field mapping and things like that, in the sense of some of these skills don't go away. The idea of thinking in 3D. How do we teach students to think three-dimensionally and solve problems three-dimensionally? So I think one of the themes that keeps popping up is, you know, we want to teach students to use new tools, but we also want to build the same fundamental skills that will help them solve problems. You know, 10 years, 20 years from now, there'll be a whole different set of problems that they'll have to solve too. And so the tools might change, but some of the kind of fundamental skill sets that hopefully they learn during their time here are going to help them solve those problems.
Talk about lab a little bit, SEM, XRF, AFM, I mean, things that we're doing to rocks.
Yeah, I think, I'm just kind of getting into this myself, but I think the analytical capabilities are much higher, and I forget how many mass spectrometers. I mean, I can't even keep track of how many actual, machines we have in these facilities, but the ability to get this data quickly and cheaply is improving quickly, and I think it's improving the quality of research that we can turn out in a short amount of time. One
of my favorite quotes was a guy that runs the SEMs out at the Bureau. He said, we're looking at shales. He said, Scott, we got our chip, and it was a cubic millimeter, and we migrated around inside of it for 2 days and never saw the same scene. Okay. So that's the level you're looking at now on these pore systems at the nano scale, and being able to go from that to what you're describing is remarkable, particularly for folks who are trying to do extractive energies. Svetlana, you've got an international perspective on all this, Russian-born and German-educated, and seen that European. But you've been leading a team now for 5 years of engineers and scientists and economists and others that have been trying to tear apart the future of shale gas and shale oil in this country, funded by the Sloan Foundation. And talk a little bit about that. We've heard today integration matters, multidisciplinary matters. Does it matter? Why is that important? And can that then be translated globally? What are some of the challenges there?
Yeah, so it actually was interesting. I was kind of thinking about what I should say in this regard, and yet the morning panel kind of brought even more questions for me that kind of I haven't thought while kind of thinking about answer to that question.
Can you use Charlie's microphone?
Sure.
That one.
Okay, so first I want kind of to summarize in 3 words what Steve was talking about. He essentially was talking about the resource, our better understanding of resource, and by resource I mean not just gas, oil, it's also solar, wind, it's climate, water, all those things. Second was the technology, and you can talk about it in different things. So we're talking about nuclear, we're talking about kind of 3D, 4D modeling, so all that kind of encompassing those. And economics, because it's a question about the cost, about what we would prefer, because economics actually, it's not just about, prices, it's also about, we like the utility function, the social welfare, kind of, we look at all those things. So, and the big visionary, which I think was in Jack's letter as I was reading it today, is really how to not just look at the geology, but really try to bring the geology into a new level. And for me, personally, the person who until 8 years ago, until I kind of get to the BEG, the geology was just looking into stones. So then I learned that one never should say stones. Yeah, so, and I never realized what geology was about. And I think what we did with our research and what the school is actually envisions and kind of goes forward to, thanks to Jack, is how to look at all these 3 things together. Look at resource, look at technology, and look at economics. And do so with better geologic knowledge, do this with better tools, do this through cooperation across different departments, different countries, different entities, including also the governmental, besides just academia, the policymakers. Do this across many different fields. And it's not easy, believe me, kind of speaking as their kind of team leader of, we now have a little bit more than 15 people in the team, so it's kind of not the world, but they come from essentially 4 different disciplines. We have geologists, and I broadly say geologists. We have engineers, and again, those are different engineers, but I call them engineers. We have statisticians and economists. It's not easy. It took us time to learn each other's language. Just as the girl who was on the first panel was mentioning, that first it takes us time to learn the language, and then sometimes we forget how to translate it back. So working in a multidisciplinary environment, we have to keep are learning not just new language, but also how to translate it back. And this was coming back to the question how we can replicate the shale experience in the world, or how we can better perform further on shale here in that country, and how we can better bring the different departments kind of working together was another question here. It's keep going back and forth with learning more and then translating it back more. So, and this is a challenge, and the biggest kind of takeaway from the team leadership was for me that we never stopped learning that, and there is no unique recipe to that, because our level of knowledge changes, our challenges change. As we learn new technologies, we face new challenges, and we are not sure that the tools we used in the past will be used. The one good thing is, I totally agree with the new PhD guy here, is we need to still keep some skeletons of the way we think and be open to do so. So that's kind of my takeaway from all this.
When you came to UT 6-7 years ago, you came out of a European model and we're working on game theory and some pretty theoretical economic stuff, and I threw you into shale and you thought you were in trouble. But you published the first results of that Barnett, and it was on the top of the full Wall Street Journal. NPR called, and we did interviews every 15 minutes for 4 straight hours when that study came out. Did that surprise you? And then in terms of impact, and again, help us translate the shale experience here globally. What are going to be the challenges briefly?
Yeah, in a couple of words, first, I still think that I'm in trouble with the work we're doing. Second, yes, actually, I'm not sure how much it questioned to me as much as Scott, who actually helps me to collate the team and all these efforts. And I'm still surprised sometimes how much impact we make, and the reason for that most of us researchers sometimes keep things narrow. We focus so much on what we do that we forget about for whom we actually do that, for the people around us and for the generations to come. So coming back kind of in a couple of words what it means, I think it's again the language and us talking openly and sometimes in a plain language what needs to be done, and not to be scared to outreach to public, not just the scientists around us. I mean, scientists are kind of good, but we actually do this for the entire community, and community is actually a final stakeholder for all that. Let's not forget about that.
And if you don't know yet, speaking of outreach, tonight is the 100th birthday or the 100th talk for Hot Science Cool Talks that Jay Banner has led and remarkably successfully. And I think Jay told me there were 1,300 registered for 1,200 seats. And that's remarkable outreach, and one of our own is going to be giving that talk. So that's at 7. Okay, Bridget, Mark Twain said whiskey's for drinking and water's for fighting. And or maybe somebody has credit. Is water really a commodity? And like oil or gas or pork bellies, and in that context, water and yes, or a commodity or not, what is it we can be doing in the Jackson School? What can we really be doing in terms? Everybody always says it's water is the next big thing. What does that mean for research and education in the coming decade here in the Jackson School?
I don't think water is a commodity yet. I think because it's considered a human right or a public good, but I think water markets are evolving as we have scarcity issues. For example, in Texas, in San Antonio, we heard Steve say earlier how much water is used for agriculture. Well, the irrigated agricultural farmers are selling water to the city of San Antonio. If they project they're going to have a drought, then the ag guys will sell the water to the city. We've seen in California this past year that the ag losses from the third year of drought were 3 billion, which seems large, but could have been a lot worse because they have an internal water market, and so the water is going to the higher value users. But so it's slowly evolving, but will take a lot of time. But I think we need to value water more highly. And if it has a low economic value, then we sort of abuse it. And we continue to have water move from agriculture to urban areas, and we see it moving in virtual water now in the food business, but we will see it more with water markets, I think, in the future. And what can we be doing? I think there's a lot of interest in global issues. We love to see global maps of everything, global modeling, remote sensing, and all that sort of thing. But at the end of the day, water is a local issue, and supplies need to meet demands at the local level. So how do we do that? We either reduce demand, increase supplies, store, or transport. And in this past year in Texas, we've certainly seen we've had floods and a very dry summer. How do we manage these extremes? Traditionally, we've stored water in surface reservoirs. I think we have full surface water reservoirs in Dallas next to an empty aquifer with the water at 900 foot depth. So we need to start storing it in aquifers, and recent legislation has improved that so that we can have aquifer storage and recovery. We're going to see more of that. And so we need more monitoring programs to understand where the water is and how long it's going to take us to recover from a drought. Are we really out of a drought? When we're in a drought, we think we're never going to get out of it. When we're out of it, we think we're never going to get into it. We need to manage these better, and that's going to be a challenge.
Sounds like oil price. Got some questions coming in here. I'll mention one thing briefly too, just in terms of technology. One of the things that we've been leading here is this Advanced Energy Consortium. It kind of applies to many of these areas where we've been trying to pioneer the building of small, smart things to put into the earth. And we're there now that we own the record for the smallest battery in the world and the smallest pressure sensor in the world. It can go to Earth's temperatures, pressures, and chemical conditions. We have a lab on a chip. It's got a battery, a sensor, storage capacity, retrievability in real time, moving it down through a pipe, and it's 2 cubic millimeters. It's just larger than a grain of sand, and it was a cubic centimeter when we started 8 years ago, so we're almost to proppant size with that. Remarkable things that are going on technologically that will give us whole new sources of information. So some things coming in. Charlie, how do you value rock core? You know, what's to 2050 and beyond? Are we just we curate more rock in this school than any other place on Earth. 2 million boxes. If you were to stack the core end to end, it would go past Denver, Colorado from here. And are we just keeping it for posterity, or what's its value out there into the future?
Well, it is one of the, certainly one of the information stores that we have that's quite unique. I mean, it is a little bit of a selective library because you do have to know how to read it. I was a little bit unhappy when we got donated the BP storage lab that the head geologist at the time said, well, we're going to give you these books. We've already read them. Yeah, I don't think so. I think, I mean, this type of information, every time you go back to those cores, you're going to learn something new. Every time I go back to an outcrop, I learn something new. Every time. And that's the kind of data that, you just can't, re-access that information. We just, Gulf oil right before one of the various declines pushed through an idea to cut a 4,000-foot core through the Capitan Reef. It's a unique data set, very spectacular. They donated it to us, and we are remining and remining that, and then the companies are coming back to us. We'd really like to see our core. Yeah, we got it, and there's way more information that we're learning now, and they're going, gee, this is really neat, because this is telling us all this information about all these other reservoirs that we don't have data for. Karachagnak, there's 4 cores, 300 feet thick, on one of the world's largest oil fields. We have data that applies almost directly to that information. So it's a unique data set. It hopefully is not going away, but it's somewhat of a thankless task at sometimes in terms of curating it. But certainly I hope it's there for the future. But like Svetlana said, we need to make people aware of that. Otherwise, it is going to be hard to justify.
Yeah, the head geologist who said that, Charlie's talking about, was a guy named Lord John Brown. He was kind of the head geologist. He's the CEO of BP. And he came right over here when Larry Faulkner let us take that facility in Houston. And we had a big deal, and the three of us spoke. John Brown's a very smart guy, but he's not very tall, and he has a very big head. We were actually recording this. I'll tell the story anyway. And my two sons 15 years ago were very young, and they were sitting right there, and Shrek had just come out. And there's another lord in Shrek named Lord Farquaad, I think, who also is small with a very large head. So my two sons were sitting there, and when John Brown went behind the podium to speak, it looked like this to them. And you could see him disappear, and they made the connection with Shrek, and they were sitting in the front row, and I was sitting right there looking out, and I could see their lips start to quiver, and I gave them the look that if you crack a smile, it'll be the last one you ever take. Great experience. And he did say that, those exact words. We have read them. So we were happy to take those books. Here's one for Steve, I think. Big data seems to be a common element across geo-research we've heard about all day. Is there a role for learning machines, artificial intelligence, et cetera, in earth sciences research? Who's working on it? Tell us just a little bit about what you're doing now, maybe, and tie that back.
Let me start at the other end, and the center that I've started in New York just about 4 years ago is meant to, I like to say, instrument a city, the infrastructure, the environment, the people. Can we acquire all manner of data about what goes on in a city, integrate it, link it together, analyze it, model it, both to do the science of understanding how cities work and to help improve cities in a very practical way. So it's the fusion of records data, it's the use of found data as might be generated by various city systems, and of course the deployment of novel sensors for sound, for emissions, for energy use in New York City. You can go through a physicist style estimate of the data rates. It's about 10 megabytes a second if you could do everything. Easily handleable. The challenge is to do something useful with it. I think the same is true generally of big data. If you know what you're doing, if you know the questions to ask, it can be wonderful. But if you just say, I'm going to get all this data and feed it into some machine learning algorithm, you're going to look pretty foolish. And so this domain knowledge is really important, and the data just becomes a tool. That said, if you look in astronomy, which to my mind is a little bit like the earth sciences because you get to watch, but you don't really get to touch. There have been great strides in the acquisition, integration, analysis of data, which has made astronomy at the forefront a much more democratic enterprise, since everybody's got access to these data sets, and also a much more fertile enterprise. Instead of just 2 supernova a year to try to understand, you can get 500 in a couple years just by taking the data that's been collected and analyzed.
We have time for 2 more questions, I think. So this is water. Bridget, throw this down toward you. Anything new or practical on the horizon for disposal, flow back, produced water, wastewater, upgrading, agricultural use, recycling, the kinds of things we can do better to get toward the ratios even that Steve mentioned in his keynote?
I guess, flow back and produced water, managing it, I think that's going to be more and more of an issue in the future. I'm not a big fan of reusing it in agriculture or irrigating with it because I don't think I would like to eat the food produced, because maybe we're not measuring some of the stuff that might be in it. So traditionally we've used saltwater disposal and injection, and talking to some of the companies in the Permian Basin, Pioneer and others, they say it costs as much to recycle and flow back and produce water and reuse it for hydraulic fracturing as it does to source new water and dispose of that. So I think the economics is becoming more favorable for recycling and reusing flowback and produced water for hydraulic fracturing. I think it's going to be a challenge that we're going to have to continue to try to find opportunities, how to resolve this. In the Bakken, they're putting most of their water back into the Dakota unit, which is shallower, and so now when they're drilling Bakken wells, they're having overpressure conditions. The San Andreas and the Permian is becoming overpressured. So, and then of course there's the issue of induced seismicity related to water disposal. So I think if the economics and industry develops techniques to recycle the water more cost effectively, I think we'll see more of that in the future.
Final question from the audience, and we'll wrap. Interesting one, good maybe to end with here. At pretty much any other university, wouldn't this panel be talking about renewable energy? What's the role in renewables? And you've heard from a physicist, Undersecretary of Energy, perspectives there. Maybe we can get an economist's perspective on renewable energy. You've done quite a bit of studies on that, Svetlana, and then maybe we come back to some geologic perspectives on it as well.
Yeah, I probably will start with just two facts. Recently there has been reported that Texas lived for several hours in a row on 70% on renewable energy. And second is that kind of we surpassed to all the European countries in terms of our capacities. And for that reason, we're currently building the Tres Amigas, line that will help to connect all the east and west grids. So a friend of mine kind of make a joke that, do you think that the east and west meets in Turkey? No, it's actually meets in Texas. But for me, that defines the future to some extent. So we will be going into renewables more and probably more aggressively as technology allows. I think with wind, we might be kind of getting close there, and to incorporate more, we either will start connecting grids and see how we can distribute that capacities more efficiently to tackle the intermittency. And on the other hand, we need to get back and struggle with their batteries and storage technology. And this includes both engineers and geologists working on this, because we have this compressed air storage idea. We have the whole bunch of different ideas that related also back to the geologic formation and geology research on that. So renewables are there. And on top of that, Steve was mentioning several times that we do need keep monitoring the weather and weather changes. And the many economists, and speaking kind of from economists, they don't know much about geology, and we like to make assumptions. Like in the past, I was making assumptions about the resource endowments on gas and oil, having no idea about the shale. So all my models that I did during my PhD had not so even hint of potential other resource. And I should say a similar thing about many current economic models on solar and wind. We keep discussing, but it's just starting kind of touching the ground now in terms of modeling, how the climate change will affect not just our demand on energy, but will also affect demand supply. So how these solar atlases and wind atlases will change with time. So we have to kind of keep looping back and updating those things.
Any economic limits to scale with renewables? Chicken.
No idea. Yeah. I would rather ask engineer. They have a much better imagination in this sense.
Yeah, one of the challenges I think too, we invited Jesse Osabel to come speak. Some of you might remember Jesse from Vision Committee at the Jackson School. He's an environmentalist at the core. He's very big on land and water are his passions at Rockefeller University in Woods Hole. He worries about density, the density of things. And so when you have things that are less dense, like wind and sun, tides and waves and geothermal, you have to make more stuff to capture them. So Steve used a 49 square mile. I think one of the challenges that we haven't gotten our arms around yet, and maybe it's good for geology, is the amount of mining that's going to go on to produce the metals, the copper, the rare earth elements, the chemicals, and handling the low density stuff And these are big machines that have to be built to capture low-density fuel. So nothing comes for free in energy. And I'd say that translates across minerals and water. We're talking about resources here, which is one of Jack's passions. Larry read it very clearly in the letter. And nothing comes for free. And the challenge of all that, of course, is scale. So it's a great question to end on, a very appropriate question to end on for the panel. And let me get you to help me thank these folks for their time today.